so this is Physics 1A 1617 for Monday, April 20th. We're going to be talking about circular motion today, as well as rotational speed and acceleration if we have time. So let's get started. So the first thing we're going to do here is we're going to take a circle. And suppose that we're describing the path of an object, okay? And the object that we're talking about could be like a ball on a string, right? And so let's say we've got a string and we draw a line from here to here. And at the end of this string, we've got a ball right here. And just imagine you're taking this ball and you're whirling it around in a string, in a circle, okay? So this ball is basically just being swung around in kind of a vertical circle like this, okay? And let's say that we want to describe some of the properties of this object, okay? The first thing I'll point out is at any moment in time, this ball, as it moves in a circle, okay? And let's specifically describe something where it's what we call uniform circular motion. And what that really means is constant speed. Not constant velocity, but constant speed, right? At any moment in time, it's going to have a velocity that we call v. And what I'd say is that if this object is actually moving it around in a circle in this direction, that at a moment in time, it's going to have a velocity vector that's going to point tangent to its motion, okay? And what I'm going to do here is we're going to say that it's moving around in a circle, and at this point in time, it has a velocity, and I'm going to call that velocity v initial, and we're going to give it a vector symbol because it is a vector. Now, if this object actually is going around in a circle like this, right, then at some later point in time, the string is going to make a different angle relative to the center, and the ball is going to be right here. And at that moment in time, it's going to have a velocity vector that's going to point straight down. I'm going to call that one v final. Okay. I'm going to make some statements about these things, but we're also going to say that, let's see, the radius we're going to call r of our circle, and the angle here we'll call theta. That the object goes from v initial to v final as it moves in a circle like this. There we go. And I'm also going to say that we can define these vectors as to be position vectors. So what we'll do is we're going to label both of these vectors here. I'm going to call this one r initial, and I'm going to call this one r final. And I'm going to make some statements about all these quantities. Since we're talking about constant speed, the velocity vector turns, okay? But I'm going to say that that vector, that velocity vector, that v initial, if we find the magnitude of it, is equal to v final. And that's just basically going to be equal to a speed that we call v. So that's going to be the speed of the object. This is just v. All right. Also, I'm going to say that the position vectors, r initial and r final, the magnitudes of these vectors, is also going to be, we'll just call that one, that's capital R. That's the radius of the circle. Okay, and now here's what we're going to do. I can make another line on this picture. Maybe I do it in like a really light green so it doesn't stand out too much. I can draw a vector that goes from the initial position down to the final position here. And I would argue that that vector, maybe if I just use a different color, I'll just use black. I can draw a vector that goes from here, its initial position, down to its final position here. And I'm going to say, it's not much room to write in here, that that vector is going to be what I would call delta r. Where I would argue that delta r, the vector delta r, is the change in position, i.e. this is the displacement of the object, right? Let me pull up Discord here on my other screen. That's the change in position of the object. And in this case, I would say that it's equal to the final position minus the initial position. That's what delta r is. Does that make sense to you guys? The next thing I would say is that if we take these two vectors, v initial and v final here, and we kind of move them and put them tail to tail the same way the other two vectors are, I would say we're going to get something like this. So we've got our v final. Let me put this over here, because there's a lot of room over here. We've got our v final vector that points this way. Right, so there's v final. We've got v initial, which points down and to the right, so I'm going to draw that one like this. That was our v initial vector. And if I put them tail to tail like this, then I would argue that we can define a similar type of delta, a change in velocity now on this part that would go this way. And I would say that delta v, the change in velocity, would be equal to the final velocity vector minus the initial velocity vector. Okay, does this setup make sense to everybody? Can everyone see this equation? Prove to yourself why that one's true, that delta r is equal to r final minus r initial. In this picture here, right, I've got a vector r initial that goes this way, I've got a vector r final that points this way, and then delta r comes from the top to the bottom, right? So you should be able to prove to yourself from some of our vector math that that is actually, that this equation is actually true. And the simplest way for me to see it is this. If I start from here, and I go up this way, I have r initial, right? It's connected tip to tail to delta r. So if I say r initial plus delta r, can you guys see based on the tip to tail method that this vector plus this vector is basically defined as being equal to this vector here? Okay, and then you just need to do one step to rearrange it to go from there. Oh, whoops, my bad. R final here, right? It should be pretty clear how you get from there to there then, right? You just need to subtract the r initial to the right-hand side. Okay, does that make sense to everybody? You don't have any questions about that? Okay, and then you can do the same thing over here for delta b. Okay. Now here's the other part about this. If you kind of investigate what's going on in this picture right here, you'll notice that there's always going to be a right angle between the position vector and the velocity vector, right? Like this is a right angle right here. That right there is a right angle, and that right there is a right angle, because the velocity vector is tangent to the circle, right? The velocity vector is tangent to the circle, so it's guaranteed that there's a right angle between the position vector and that, right? As a result, if the position vector moves through an angle theta, I would say these velocity vectors also move through an angle theta as well. The exact same angle theta here and here. Just for people watching, here and here, those are the same angle basically, right? You can convince yourself that that's true. I'll give you guys a minute to kind of think about that to make sure you understand why that's true. That this angle and this angle are the same. Can you guys see it? Does it make sense? If you're confused, it's totally okay. Okay. So now what we can do is this. We have two triangles that are what I would call, well, I'll ask you guys to remind me. If I have a triangle that has this side equal to this side, and another triangle that has this side equal to this side, they're both isosceles, right? They both have the same angle at the top, right? What can you say about these two triangles here? They're similar by side angle side. That's exactly right. Well, yes. Yeah, they're similar. So, similar triangles. So since they're similar, we can make ratios amongst the sides, right? For example, if I take the side that's opposite the angle here. So on the left-hand side, what I'm going to do, I'm going to say delta V divided by, really either of these sides work, but I'm going to use, let's say, V initial. But I can't divide vectors, right? I don't know if you guys know this. You actually can't put vectors in the denominator of an equation. Division by a vector isn't really defined, okay? So instead, we can only really use the magnitude here if we put it in the denominator. It's okay to leave the vector symbol on top in this case. I think. We'll see where that goes. I know it's okay to put vectors in the numerator. In this case, I think we might actually end up looking at just the magnitude. We'll see in a second, though. So then, on the right-hand side, that's the ratios of this side to this side here. Delta V over V initial. On the right side, we'll look at the other triangle. So we're going to take delta R over R initial. So delta R divided by R initial. That ratio should be, the ratio of the change in velocity to the velocity should be the same as the ratio of the change in displacement to basically the radius, right? And I want to throw one other thing in here. Let's say that it takes the time delta t to go from here down to here. That time interval we're going to call delta t. Now we're going to rewrite this equation by doing this. We're going to say, we said before that V initial magnitude was equal to V and R initial magnitude was equal to R. So this equation can actually be written like this. Delta V divided by just V, the speed, should be equal to the change in position, the displacement, divided by R. And now what we're going to do is we're going to multiply both sides by 1 over delta t. I think we are going to have to take the magnitude of these vectors too. Yeah, we'll see. So we end up getting, on the left-hand side of the equation, this is what we end up getting. We're going to have delta V over delta t. This is going to be equal to, I'm going to take this V and move it to the right-hand side. So we're going to have delta R divided by delta t. Why is it so hard to write a delta? It's just I'm kind of low on this pad here. Delta R over delta t. We're going to multiply by the V from the denominator here. And we still have an R from before. Now we can think about what these things represent right here. What does delta V over delta t represent? Exactly. So this would represent, very specifically, this would be the average acceleration, right? What about delta R over delta t? That would be equal to the average velocity. But in this case, the average velocity is just v, right? Now, in this last step here, I'm actually going to have to remove these signs. Okay, but I want to point something out really quickly here. The direction of the average acceleration, right, is in the same direction as delta v over delta t, right? So now we can go and look at our picture real quick here. The direction of the average acceleration points in the same direction as delta v, right? What direction does delta v point? It points like that direction, right? Right, that's where delta v points, right? So if you look at your picture, effectively this, draw with a different color, the direction of the acceleration vector is basically pointing towards the center of the circle then. That's the direction of the acceleration. Is it points from here down to the center of the circle in the same direction as delta v. So this type of acceleration has a name. We call it centripetal acceleration. Now coming down here to finish this up, I'm basically gonna do one other thing here. You can see from the picture or from this equation that the direction of this is given by that, but now what we're gonna do is we're just gonna find the magnitude of these things. Because then we can get rid of this symbol here, and we can say basically that A average is velocity times velocity over R, and to then kind of like drive that home, what we end up getting is that the acceleration in this case is equal to the velocity squared divided by the radius. This type of acceleration is called centripetal acceleration. The word centripetal means center seeking. It means it points toward the center. Do I have to write center seeking? I don't have to write that, right? I'll just say that this type of acceleration, it always points toward the center of the circle. And we usually put a little c right here for centripetal acceleration, and it's given by the velocity of the object squared divided by the radius. So all of this is really just a derivation, and if you got kind of lost in all these symbols that I'm using and stuff, I understand. This is what you really need to know. When an object moves in a circle, there's going to be what we call a centripetal acceleration, and it's given by the velocity of the object squared divided by the radius, or really the speed squared, right? So there we go. Do you guys have any questions? It's kind of neat, I think, this proof. I don't know how much you guys like proofs, but I like geometrical proofs, and I like the fact that it uses similar triangles. You don't see this used very often in really anything, to use similar triangles to kind of prove something. So do you guys have any questions before we keep going? So now let's just say something in general about this. So for an object that moves with uniform circular motion, so again, these are the words: uniform, circular, motion. When an object's moving with this type of motion, you have a circle, right? Here, let's actually use the shape, because it really is nice to actually have a circle for this. You have a circle, and you've got an object, and at a moment in time, it may be moving with some velocity that we call v, and what we're saying is there's going to be an acceleration that's going to point towards the center. Oops. An acceleration that points towards the center like this. When the object, for example, is, like, let's say right here, it's going to be moving this way. The acceleration is going to point also towards the center of the object. And if this acceleration is produced by a force, which it has to be, right? Like, for example, if we have a string, and it's connecting between the center of this circle and this point right here, then the other thing we can state about this is that there's going to be a force that points along that string that produces the acceleration, right? And that force could be tension or something like that, for example, right? And if that's the case, this is what we can state. We can say that if we sum up all the forces that act along the radial direction, this should be equal to the mass of the object multiplied by the radial acceleration of the object. And what do I mean by that? I mean, you construct a coordinate system so that this is the r direction. This is the r direction, okay? It always points towards the center, okay? That's the r direction over here. It always points towards the center. Then, if you do that, you can state that if I take the forces acting in the radial direction, which in this case would be the force of tension, that force of tension should be equal to the mass of the object times the radial acceleration. But in general, we'll say that this radial acceleration is the same thing as centripetal acceleration, so it's going to be equal to v squared over r. You're going to see both of these type of languages. You're going to see radial acceleration and centripetal acceleration both used. Your book likes to use radial a lot. And I know that it's not just your book, a lot of teachers do too. So in this case, if this is what the acceleration is, then the tension should be equal to the mass times the velocity squared divided by the radius. This is the kind of thing we're going to be using to allow us to use Newton's second law to solve problems involving objects that move in circles. Not just objects that move in circles, but objects that move along paths that can also be circular, right? Like, for example, a roller coaster, right? Where an object goes down and it kind of goes in a circle like this. At any point in time, the motion of this object can be described based on the this type of circular motion, and we can say that it has this type of radial acceleration. Oh, I want to mention one other thing right here, by the way. This velocity in this case is a tangential velocity. All right? It's a tangential velocity. That means it points tangent to the circular path. Okay. And in this particular case, it has no tangential acceleration. That's pretty much the theory. We're going to use this to solve a lot of different types of problems. And, you know, if you guys have any questions in general, let me know. One thing I do want to point out here is you need to be careful about the words. This word right here, centripetal, this is not the same thing as the word Centrifugal. These are not the same thing. You're going to see this word used. You need to be careful about every time you see this word. This word is a very loaded word. Centrifugal. So be sure to... These are not the same thing. Okay? In terms of circular motion, I kind of want to talk to you about one particular situation, just to kind of relate this to you guys. It's something maybe you've seen before. So, have any of you guys ever ridden on a ride at an amusement park where this is basically how it's set up? You've got a large cylindrical container, and this cylinder is rotating about an axis that runs through kind of like this. The whole object kind of rotates like this. And then on the inside of this object, you have people, right? So for example, over on this wall on the inside, you may have a person, and their body may be kind of up against the wall here. You may have a person that's over here, right? And the whole thing basically starts to spin. Have you guys ridden rides like this before at amusement parks? And like, what do you notice when you ride in a ride like this? What do you feel as the object starts to spin faster and faster and faster? What do you feel on your body at this location here? You feel being pushed into the wall. That's right. Yeah, that's exactly. You feel pushed into the wall. Pushed back into the wall. Okay, Dawes says the normal force of the wall. That's a very good way of putting it. You feel pushed into the wall. Really what you're feeling, as Dawes says, is you're feeling what's called a normal force, right? The wall pushes on you, and so you feel pushed into the wall, right? That's how it works. I was going to ask you guys, what force are you feeling? Okay, someone already answered it, but does anyone else have another idea of what force do you actually feel here? The question would be, do you feel a force that points this way? Or do you feel a force that points this way? What do you feel? Does it point left or does it point right? It feels like it points away from the center, right? Jesus is saying inward. It does feel like it points away from the center. It feels like you're being almost like flung off of the machine, right? But in reality, it's this one here. And that's because of the acceleration. Jesus is exactly right. He's thinking about this in exactly the right way. So you feel a force to the left because what's going on is that you have to identify forces coming from real actual things. And the force in this case is the normal force, right? You also feel some other forces, right? I mean, you have a weight that goes this way, right? And there's going to be some type of a friction force pointing this way, right? But the normal force, right, is the one that if I say that I sum up all the forces acting on this system in the radial direction, okay, and this is going to be my radial direction pointing toward the center, then I'm going to say that that should be equal to the mass of my object times the acceleration of the radial direction, which is m times what we just learned, velocity squared divided by the radius, where the radius is now going to be this radius here. And the force you feel is actually the normal force. And the faster that you go, right, as v increases, the force you feel increases as well. Right? Your mass doesn't change, the radius doesn't change, but as it spins faster and faster and faster, the normal force goes up, and so as a result, that leads to what you actually experience. You feel pushed into the wall. And to be 100% clear in this case, the acceleration also points in this direction. That's the direction of the centripetal acceleration. Or the radial acceleration, or whatever you want to call it. So it seems like you're being pushed to the right, but you're actually being pushed to the left. Because what you're feeling is the force of the wall on you, but you think it's the force of you on the wall that you're feeling, which is really kind of weird. I'm not trying to confuse you or anything, it's just... You naturally think in this kind of situation that you're being forced outwards, but in reality, you're being pushed inwards. If that makes any sense. It's your inertia that makes you feel like you're being pushed outwards. We'll talk more about that as we move on to some of these other questions here. Okay, does this? You have a question, Jesus? That's crazy. Yep, that's crazy. Exactly. All right. I can give you another example of this, but it'll naturally come up as we're talking about some of these problems. I don't want to, kind of do a problem, talk about how we analyze these things. So I want to start with, we're going to do 4 and 5 first. So we're going to do this one first. Okay. So here's the problem. Man, this feels like a really hard problem to start with. But should be fine. I mean, you know what? It is too hard to start with. I don't want to confuse you guys. Gotta make sure we kind of build on things. I don't want to be too confusing. Here. We'll do this one first. So here's the problem. A ball of mass m at the end of a string of length L is moving a horizontal circular motion at a constant speed v as shown. So this would sometimes be referred to as like a conical pendulum. Right? The motion of the pendulum is in a circular motion, like around like this. It's going around in a circle like this. But the kind of the string plus that bottom ring basically traces out a cone. It traces out an object like this, right? That's the path that it's going on. So we call that a conical pendulum, and we basically want to relate all of these values. Our goal here is to find an expression for theta, the angle theta, in terms of the parameters shown plus g. Okay. Roller coasters are fun. Yes, I totally agree. It's been a couple years since I've been on one, but they are really fun. So here's what we're going to do. We're going to draw our picture, and we're going to label our forces acting on our object. It's always how we do these kind of problems. So in our picture, we need to indicate what the angle theta is right here. And r, which is this distance here. And then there's our ball. We can draw the forces on the ball really at any point in this motion that we want to, okay? We know this length is L, and we know it has a velocity v, as we can see here. So I would say let's draw forces acting on this object. What would the forces acting on the ball be? I need to make this one thicker. So tension, right, which goes up this way. It says the ball has a mass m, so our weight is just going to be mg. Okay, what else? Can you guys think of any other forces? There could be air friction, like drag or something, but we're not going to worry about that. Other forces that you guys can think about? So the Physicsinator says a centripetal force. Where would I draw such a force? So I need another force here. You want to call it FC?
Do we draw that force vector?
I don't know. What do you guys think?
I mean, it should vector be this.
Sorry, yeah, B, it's not on a surface. Basically, the idea is you got a ball, and it's just going around in a circle like this and this. Like, you could do this yourself. If you took I don't know, anything, like, you could take your headset, you could take, like, your, wait, you guys all have, like, wireless headphones now, don't you? I was going to say, if you took, like, your earbuds or a necklace, yep, and you just, like, whirl it around in a circle, does that make sense? Sorry, sorry, there's no surface here, by the way. It wasn't really clear. It's just, like, it's at the end of a string, and it's just moving in a circle like this. Like, again, like, You basically just have something that instead of pendulum, instead of swinging back and forth, it's like swinging around in a circle. Can you guys all imagine that? If not, I can describe more. I could probably find a video of a conical pendulum. Let's see. Can we get one that's not just a physics problem? Maybe just like a video of something like this? This is probably good enough, I guess. Like that. There we go. That's pretty good, actually. Yep, that's what's going on. Going around in a circle just like that. That's a really nice picture, actually. That's cool. All right. You know, what is this PBS Learning Media? There's some good stuff on here. What is this one? I have to look more at this. They maybe get some good things for us to work here. Segway technology. I don't even know how segways work. Well, I kind of do, but... Huh. I need to come back and look at this website and understand more. They're doing all education for homeschooling. So I know you spent like 30 minutes driving it, but where does the centripetal force come from again? So, you know, there's no such thing as a centripetal force, actually. It's not a... You know, what I was trying to tell you is... I got caught in the middle of this, but this last force I drew here isn't real. There is no centripetal force. It's not a real thing. Centripetal force is just... It's kind of a bad word. There is such a thing as centripetal acceleration, but a centripetal force would just be like any force that drives an object toward the center. Okay? So there is no extra force. This is it. Those are the only forces. And the thing I wanted to emphasize by asking the question about if there is another force is... to emphasize that all the forces that produce circular motion are the same as the forces that we've seen before. We're not introducing any new forces at this time. Does that make sense? All we're doing is taking the same forces that we already know about, things like tension, friction, weight, spring force, that kind of thing, and we're going to see how those forces produce circular motion, okay? So centripetal force doesn't come from anywhere. Centripetal acceleration just comes from the fact that when an object moves in a circle, it has to have an acceleration towards the center to bend the object in a circle. Does that make sense? In order to have something that moves in a circular motion actually move in a circle, it must have an acceleration that points toward the center, right? Because effectively what's happening is that as the object moves, this velocity vector is being turned this way perpetually, right? The velocity vector is constantly being turned, and it's being turned by the centripetal acceleration right here. This is exactly what's going on, you know, with the sun and the earth, right? The sun at the center produces a force on the earth that allows the earth to move in a circle, right? The earth at any moment in time has a velocity vector this way, but it's subject to a force of gravity that goes this way, right? And that force of gravity produces a centripetal acceleration. So asking, you know, where does the centripetal force come from? In any given problem, if it's the earth and the sun, the centripetal force would be the force of gravity. In a problem where you have a ball on a string, it's the tension, right? Okay, so does that answer your question, Ash? And then, okay, cool. And then once you have the quote centripetal force, that force is the thing that actually produces the acceleration. This is something, in this case, it's R. Okay, R is a radius. It's not a force, by the way, sorry. This R is just a radius, it's not a force. All right? The important thing to understand is that centripetal acceleration is produced by all the normal forces you know about. You don't need to add additional forces onto your diagrams. I would say, as usual, we do want to kind of indicate that the acceleration of our object is this way. And keep in mind that that means that we're going to make that our positive direction when we're analyzing this. Okay. In this case, what is the thing that actually makes the object move in a circle? Can anyone tell me? What's the force that produces this acceleration in this direction? It's the tension. It's the component of the tension that's parallel to the radius, right? Yeah, exactly. So just keep that in mind. That's the most important thing about this. Yeah, the x component, exactly. The most important thing about this is, like, circular motion is no different than the type of motion we've seen before, in the sense that it still obeys Newton's second law. Newton's second law states net force equal to mass times acceleration, right? And circular motion is no different. The only difference is now we have this new type of radial acceleration where you get mv squared over r. That's it. That's really the only difference. It's not anything new. But the problem is that you still have to kind of think about in your brain what it means when something moves in a circle, and that can be kind of tricky. All right, so let's solve this problem. What I'm going to do is I'm going to make the radial direction point this way. I'm going to call this the positive r direction for radial. And then we'll make the upward direction the positive y direction. And what we'll do is we're just going to say, just like we've done in the past, we'll say net force acting in the y direction has to be equal to the mass of the object times its acceleration in the y direction. And then if we add up all the forces in what we call now the radial direction, those are going to be equal to the mass of the object times its radial acceleration. All right? In order to do this, once we've picked our axes, right, we do need to break up the tension force into components. So one component is going to go up like this, and then the other component's going to go over like this. And maybe we can get rid of that L right there. And then you guys know how to break this up, right? Like, this angle is going to be theta. This is going to be t times the sine of theta. This is going to be t cos theta. And yep. Let's do the y direction first. We only have two forces in the y direction, here and here, right? We're making up positive, so this would tell us that t cos theta minus mg should be equal to. So if this object is in fact moving in this kind of circle like this, right? What would we say about its y? What's going on in the y direction? Does the y coordinate of this object change? Yeah, its acceleration 0 because its y component doesn't change. So then you get 0 right here. Right? So then we can solve this and just say t cos theta is equal to mg. Okay? In the radial direction, we only have this one force, which is t sine theta. And so that has to be equal to mass times its radial acceleration, but it's moving in circular motion, so that's going to be mv squared over r. And now our goal was to find theta. So we can just solve this. We can eliminate t. Take this and plug it in over here. And we can do some rearranging here. The masses are going to cancel. And we end up getting what? G tan theta. Because sine over cosine is equal to v squared over r. Which means that tan theta is equal to v squared over rg. And then obviously you could use that expression if you wanted to define what the angle theta is by taking the arctangent of these things here. We could pick some values too and see if it, what would happen. What would happen if theta was equal to 0? Oh, well, actually, wait a second. Did that derivation make sense to you guys? You guys notice any mistakes I made or anything? Any questions? Or so if theta equal to 0, what does that mean that v is equal to? Now, yeah, because tan is 0, 0. Does that seem reasonable? That if the angle is 0, right, the object would just be hanging like this, right? Not like that. But the object would be hanging straight down. And yeah, the angle would be 0, the velocity would be 0, right? That's equilibrium, right? Okay, and if we pick another kind of ridiculous value, what if we pick theta equal to 90? What happens to the velocity then? Yeah, so this is impossible, right? It's impossible to swing an object in a circle like this. You can try it yourself if you want to, with the angle being exactly 90 degrees, right? What that means is, suppose that you, so here, this is a similar problem. Suppose that you take a ball on a string, right? And you're holding it like this, right? And you try to do this. You try to basically make it so that the ball is level with the ground, and it just kind of and it moves around in a circle that's like this, okay? But you try to make it so that the ball is, so that circle is completely horizontal with the ground, right? What we just proved is that's impossible. It's 100% impossible to do that. There will always be, you can never do that unless you can move it with an infinite speed, which is obviously impossible, right? So it's always going to be the case that there's going to be a tiny, tiny angle, or I should say a large angle, right here. that angle, the maximum it could ever be would be like less than 90, basically. You know, it's never, if this angle can never be, like theta is basically always has to be less than 90 degrees. There's always going to be a slight deviation here. Why? Because of gravity. Because gravity pulls down on this object. And no matter how hard you swing it, you can't outpace gravity with the way that you're doing this, basically, if that makes any sense. Gravity will always make it so that there's a small, tiny little dip below this angle right here. You can try it yourself if you want to. You know, take a ball on a string and, you know, swing it above your head, and you'll notice that there's always just that, like, little tiny angle right here. It could be 1 degree, 2 degrees. It's more likely to be like 10 degrees. Yeah, it doesn't actually even depend on the mass of the ball, right? It only depends on the radius of the swing and gravity. You guys have any questions? Nope. Can't be greater than 90. Cannot be greater than 90. A different angle? Yeah, so we could pick like, if we pick another angle and we actually want to see what it's going to be. So if we, for example, choose, here's an easy one. If we take theta equal to 45 degrees, then the velocity is going to be equal to the square root of RG. And so, for example, if you take r equal to, let's say, I don't know, 10 meters, and then use g equal to 10, then r would be equal to 10 meters per second. Nope, 10 meters, my bad. Oh, v. V would be 10. Yeah, that's right. It's just v equals 10 meters per second. Does that make sense? Okay, so that's kind of a nice introduction problem to circular motion. And we're at 3:08, so this is probably a good time to take a break. But if you want to think about something during the break, this is what we are going to do next. We'll do this one, and then we're going to follow it up with the other problem down here. Any other questions before we go on break? Okay, we started class with quite a few. I'm going to stop recording real quick.